Why does a rim point of a small circle rolling inside a fixed circle trace a straight diameter? The cause is at the no-slip contact. Let the small circle radius be little r, and the fixed circle radius be capital R. The small circle's center orbits at radius capital R minus little r. Theta measures that center's counterclockwise orbit. Phi measures the small circle's clockwise spin. With no slipping, the center arc, capital R minus little r times theta, equals the rim arc, little r times phi. When capital R equals 2 little r, phi equals theta. So the orbit and spin cover equal angles in opposite directions. Call the tracked point P and the small circle's center C. The position vector of P is the vector to C, plus the vector from C to P. The vector from the fixed center to C has length capital R minus little r and angle theta. The vector from C to P has length little r and clockwise angle phi, fixed by no slip. When capital R equals 2 little r, both vectors have length little r. Their angles have equal magnitude in opposite directions. So P has horizontal coordinate 2 little r cosine theta and vertical coordinate 0. The 0 keeps P on the diameter, while cosine carries it from negative 2 little r to 2 little r. The collapse is fragile. Move capital R from 2 little r to 2.05 little r. The center vector grows to length 1.05 little r. The rim vector now turns clockwise through 1.05 theta. The vertical coordinate is now 1.05 little r times sine theta minus little r times the sine of 1.05 theta. It is 0 at some angles, but not all. The residual height bends the line. At 2 to 1, the coupled length and angle conditions match at once. Let capital R over little r be an integer n. The center vector has length n-1 times little r. The rim vector turns n-1 times as fast in the opposite direction. At a sesame, the tracer reaches the fixed circle. So the two vectors point in the same direction. The center vector has turned counterclockwise through theta, while the rim vector has turned clockwise through n-1 times theta. So n times theta equals 2 pi times an integer. One center revolution contains exactly n cusps. At 3 to 1, the tracer draws a 3-cusped deltoid. At 4 to 1, it draws a 4-cusped asteroid. At 2 to 1, there are only 2 opposite contacts. The 2 branches retrace the same diameter, producing the degenerate line segment member called the 2C couple. Add gear teeth to both circles and reverse the power flow. A piston now drives the tracked point along the diameter, while the 2 to 1 gears produce rotation. The same geometry appeared in Matthew Murray's engine design of 1802. A surviving engine built around 1805 worked at Bradley's foundry until 1931. The material has changed, but the mathematics has not. The fixed internal ring gear has twice the pitch radius of the rolling pinion, and the marked point remains on a straight path. 2 circles do not magically make a line. One exact ratio makes the arm lengths and their opposite turns match. Change the ratio and the mechanism draws a different curve. Keep 2 to 1 and it converts between rotation and straight line motion. Subscribe for more math made visible.